mean, because they can sometimes have different connotations in what we think they mean, okay? Oh, that thing is in the way. Well, that's annoying. Okay, I'll just tell you what goes there. That will not go away right now. Okay, so spectroscopy, okay, is the study of the absorption and emission of light by radiation of matter, okay? So the term radiation, I would say, typically has like a negative connotation, right? Like when they talk about radiation, it's not something that's good. But in terms of scientific definition, radiation is any sort of energy that is a type of light. And the electromagnetic spectrum are all the different types of light/radiation that exist. So in a sense of being like, oh, people are like, oh, don't get exposed to radiation. We are always exposed to radiation, right? Radiation is always there. Now there's various types of it, whether it's dangerous radiation or harmful versus not. But in terms of just in general, like you're being exposed to radiation from the lights above you, through the window, from your cell phone, right? The Wi-Fi, like it's all types of radiation, okay? This blink right here is the electromagnetic spectrum, okay? So the electromagnetic spectrum is a form of energy that has wave-like characteristics, and all types of waves travel at the same speed, which is 3.0 times 10 to the 8 meters per second is what the M per S means. So meters per second, which is the speed of light. So all light, no matter if it's radio is a type of light wave because it's a type of radiation, right? Or gamma, they all travel at the same speed. So when we're looking at their different, you could say, abilities of why radio waves do one thing and X-rays do another and why some are more dangerous, does it have to do with how fast they're traveling? No, because they all travel at the same speed. So it's not that X-rays hit us faster. So there must be something else that's causing them to interact with us differently, okay? So let's take a look here at the parts of a wave, okay? So this is our first I can for today, is to identify the parts of a wave. So the 3 vocabulary words you need to identify are wavelength, frequency, and energy. And then the second part of I can is connecting it to the electromagnetic spectrum, okay? So wavelength right here, after you fill it in, if you want to highlight it on the diagram that's on your paper, right? So wavelength is given right here. It's the distance from either crest to crest, crest meaning the top of the wave, or trough to trough. Okay, so it's the distance between, and notice it's going to be the same because waves are symmetrical, right? They don't change. The wavelength would stay consistent. Okay? Now, the frequency of a wave is a little bit harder to model because it relates to the movement of it. The frequency of a wave is how many cycles it goes through in a second. So in this case, notice right here, so here's the second part. So this isn't the frequency, but it's part of it. Okay? So a cycle is up and down, right? So this goes through 1, 2. So in a sense, we would say the frequency of this wave is 2 because it went through 2 cycles in 1 second. My unofficial definition of the way I visualize frequency, of like how it would look, is I think of it as the squashiness of the wave, right? A wave with a high frequency, like this, is really squished, right? So this is high frequency versus if it's more spread out, right, then that's going to be a low frequency. Okay? Now let's understand the connection between the two of them. Okay? So imagine with me, everybody, here's my analogy with a wave. Okay? So imagine my head has a marker attached to it. Maybe I should make a hat like that one day, and then I can do it for well. Okay? So imagine my head has a marker attached to it, and I'm drawing a picture with my head. Okay? If I have a long wavelength, that means I'm going to be taking big steps, and see how my head is like making a wave. Can see that? Right? So long wavelength versus short wavelength, right? Then it's like, what's the connection between wavelength and frequency? Are they directly connected, meaning as one gets big, the other gets high? Or are they inversely directed, meaning as one gets big, the other gets small? Anyone have an idea? Oliver?
I mean, if it's high frequency and low wavelength, it would be like really high all the time. So I think it's probably the opposite.
Yes, they are always inverse. It's impossible to have a wave that has both a long frequency and long wavelength and a high frequency. Okay? Once again, here's an analogy for you. Okay? You see it. Sorry, it's a stereotype, but stereotypes exist for kind of a reason, right? To some extent, right? So imagine with me, you have your really tall basketball player, okay? And they always seem to have their very short girlfriend. You know what I'm talking about, right? Okay? So, if they're walking together, the tall one has a long wavelength and a low frequency. In order for their short girlfriend to maintain with them, right, they have a short wavelength, but a high frequency, right? So you can kind of like imagine it by like stride length a little bit. Okay? Questions on those definitions of frequency and wavelength? Is frequency, now the one thing I want to question here, is frequency the speed that's traveling? No. Because imagine those two people, they're going at the same speed, right? They're walking together, but their cadence and their steps are different from each other. Okay? But don't mix up frequency with speed, because everything travels at the speed of light. Okay? What the? Okay. There's pictures on that. I don't know where they came from, but they're not supposed to be there. Okay, take a look at the box right there, and we're going to draw two pictures with me. I kind of already gave you some examples, but I want you to, on the first one, I want you to draw a wave that has a longer wavelength than the one pictured above. So here's my picture. In your box right here, draw me a wavelength that is longer than that one. Because it's a little bit of a comparison to just use the term long or short, right? Like longer than what, shorter than what? So in that first box, draw me a wave that has a longer wavelength than the one we highlighted. Give me a pencil drop when you're done. Then in the box next to that one, I want you to draw me a wave that has a higher frequency than this one. So draw me a wave that has a higher frequency than this one. And then we'll check our answers for two smiley faces. Good, guys. Oh, it's maybe getting, is it getting a little brighter? Oh, there's like, okay, we might make it. Okay, check up here, everybody. Now, obviously, answers can vary. But once again, on the first one, you should have drawn something that is more spread out. So have a smiley face if you did that. And then you should have drawn a more coiled up, squished one for high frequency. So have a smiley face if you have that. Questions on frequency and wavelength? Okay, eyes back up here, everybody. Now, we already answered this, but let's put it on our paper. Which wave travels the fastest? Good. Trick question. It's the same. All waves travel at the same speed. right? Having a higher cadence doesn't mean you go any faster. It just means you have less space between your steps. Okay? Now, energy is our final piece we want to connect it to. Energy and frequency are directly related. So the higher the frequency, the higher the energy. So this wave would have a higher energy because it has the highest frequency. Okay? All right, let's take a look now and connect this to our electromagnetic spectrum. Okay? So the electromagnetic spectrum, once again, shows all the types of full range of radiation that I'm going to say we know exist as humans. Right? Because science is always evolving, and so who knows, there might be more past this that we just haven't discovered yet. Okay? What I want us to note first, okay, is starting, so down here on these arrows, we're going to fill in what's going up and what's going down. So if I'm going in this direction, notice that wavelength is getting bigger. So this direction has increase in wavelength, which means the opposite side has an increase in energy and frequency. Because those two are directly related, wavelength is inversely related. Okay, so our goal is to understand how each of the different parts, if I'm comparing them, how does radio wave, UV, all the different ones relate in terms of energy, frequency, and wavelength. If I give you two of them, based on this, you should be able to compare. Now, even though you may now have it memorized because of that lovely song, you will be given a diagram like this on the quiz because, once again, this class isn't about memorizing. It's just about using and applying knowledge. But making sure we understand how it's connected through these three words. Okay? All right, any questions so far on that? Okay, what we're going to do now is we're going to do 3 different experiments to kind of understand how these other types of radiation came to be.